Hello, welcome for this second module about the design of cold form profiles. The first module was about the technology and the principle. This second module is about the different ways to make calculation with cold form profiles. During these modules, we will study the mechanical model to take into account of a local flange instability. We will study also the mechanical model to take into account of a local web instability. We will see the formula to determine the span bending of a profile sheet. We will see the formula to determine the end support reaction and the intermediate support reaction. We will demonstrate the formula to determine the interaction between the support bending and the support reaction. We will find a formula to determine the shear resistance of the sheeting. We will study also the liner tray and the perforated sheet. We will see how to deal with the deflection criteria that are defined in the Eurocode. We will see all the cases that are not already covered by the Eurocode, and for this profiles, it will be necessary for you to go at 9 over E lectures to study these specific profiles. Now we are going to study the mechanical model to take into account of the local flange instability. First, the notation that are used. On the top, on the right, you can see a typical trapezoidal product. We have B and this R, that is the distance between two consecutive ribs. We have BB for the bottom flange and B and this T for the top flange. And we have H or HW for the height of the profile. On the left, you have some details. You can see that in the cold form profile, we have corners and angles in this corner. In function of your calculation, you can take into account or not take into account of these corners. In function of that, you have different dimensions. You have B, that is the global length of the plate, and BP, that is the reduced length of this plate. It is, in fact, the plate part of B. You can see also on the web that we have H, the total height of the profile, HW, the distance between the centroid of the plate, and SW, that is the pitch length of the web. We have also some notation for the liner tray, and we will see in detail this after. As I said, when you make a design by calculation following the Eurocode, you have to follow the field of application of the formula. And here, you have an example in table 5.1 of the Eurocode that explains you this criteria that must be applied. For the flange, on the bottom of the table, you can see that the ratio B divided by T must be inferior to 500. For the web, you have another criteria in function of the degrees of pitch of the web. As I said before, you can take into account or not taken into account of a corner. If the radius of this corner divided by T is inferior to 5, and if the radius is inferior to 0.10 BP, in this case, you can neglect the corner when you design the profile, and in this case, the profile is assimilated at a sum of plate elements. Okay, now we go in phases with some theories. We will study a plate buckling, and we will see what are the buckling loads that create this buckling. So on the top, you can see a plate element. The width of this plate element is A, the length is B. A load is applied, a normal load, Nxx. And we have T, the thickness of the plate, E, the Young modulus of this plate, D, the rigidity of this plate, and you have the formula on the left, and nu is the ratio Poisson. If we study this plate, we have the four-order differential equation that is given here. In this equation, W, function of x and y, is the deflection of this plate. And again, you find Nxx, the normal load applied to this plate. The aim of this calculation is to determine the N critic, the load that creates a buckling of this plate. In fact, the solution of this equation is given here. W, function of x and y, is A, and this Mn, double sinus, in function of M, N, P, X, A, and B. If we introduce this equation inside the differential equation, we obtain this equation in double square. We have another equation that gives, in function of Nxx, the stresses. In fact, Nxx is equal to the stress sigma xx multiplied by 2. So Nxx is equal to the stress sigma xx multiplied by T, the thickness of the plate. Now we would like to find the buckling load. To find this is easier. We have to derivative this expression. and the derivative must be done in respect to m. So we take this expression, we derivative to m, and we obtain, if we put this derivative equal to 0 to have a minimum value of a buckling load, m must be equal to a divided by b. If we put m that is equal to a to b in this equation, we obtain the critical load n critic. That is equal to 4 multiplied by d, the rigidity of the plate, multiplied by p squared divided by b squared. So we have a possibility now to explain, to define a buckling critical stress, and this buckling critical stress is given here. Sigma critic is equal to k sigma multiplied by p squared multiplied by E, the Young modulus, divided by 12, divided by 1 minus nu square, multiplied by T divided by B square. It's a famous equation well known by the engineer. One point important, when we make the calculation, we obtain 4. You can see this at the beginning of the formula. In the Eurocode, this coefficient is generalized and replaced by k sigma. And k sigma will take the value 4 when the plate is uniformly in charge. Okay, now we are going to study the effective width notion and the determination of the rho coefficient. On the top on the right, we have a sheet in yellow, and this profile sheet is submitted to a downward loading. Due to that, these profiles are flanged in compression. It is in red. In this area, the profiles are submitted to local buckling. You can see the distribution of the stress corresponding to this local buckling. And the corresponding critical stress, sigma critic function of B, is given. The engineer prefers to work with a simplificatory situation. And we would like to work with sigma critic function of B effective. B effective is a new length, and with this length, the stress is uniform. And the value of sigma critic is equal to Fy. The question is how to determine B effective. B effective is equal to rho multiplied by B bar. Now the question is, what is rho? And we will see after how to determine it. Okay, now we are going to determine the plate buckling critical stress. We know that the critical stress function of B effective is fixed to Fy. And this gives a formula that was determined in the first slide. In fact, this formula can be simplified with a k coefficient multiplied by the ratio T divided by B effective at square. By dividing the critical stress by Fy, we obtain this formula. If we continue, by calculating the square root, the above equation becomes this formula. If we multiply by B, we obtain this expression. In fact, what is interesting is the ratio between the critical stresses calculated for B effective and B. And here you can see this formula. By some mathematics, we obtain an expression of B effective that is equal to B multiplied by the ratio sigma critic of B divided by Fy, and we take the square root of this. We take the reverse equation of this expression, and if we multiply by the ratio B divided by B effective, we obtain this expression. Okay, we have this expression, and now, in link with the Eurocode, we defined a critical slenderness, lambda bar P, that is equal to this expression, B divided by B effective, and that is equal, in fact, at 1.05 multiplied by the ratio B divided by T multiplied by the square root of Fy divided by E divided by k sigma. So now we are going to determine the critical slenderness. We define epsilon. In fact, in the past, the tests were done with a yield stress of a raw material that was of 235 megapascal. Of course, today we have Fy that is above this value, and the value is 400 megapascal. To take into account of this evolution of raw material, we explain now that Fy is a function of epsilon square. And we add this value, and we replace the value of Fy in the expression that we obtained just before. By this approach, we can define now a slenderness, lambda p bar, by the two expressions that are given here. And if we use the fact that we know the value of E and we know the value of the ratio Poisson of 0.3, we obtain a new value of the lambda p bar that is exactly the formula given in the Eurocode. In 1910, von Karman proposed a method to determine B effective. I remember you that B effective is equal to rho multiplied by B, and we try to obtain this value of rho. Von Karman said that if lambda p bar is inferior or equal to 1, in this case we have no buckling and rho is equal to 1. If lambda p bar is superior to 1, in this case rho is equal to 1 divided by lambda p bar. After some tests, Winter, in 1947, proposed a new value of a factor rho, and is given in this formula. Finally, after several testing, calibration, we obtained at the end the following formula of a ratio B divided by B effective, that is equal to rho. Okay, now we arrive at the expressions that are given in the Eurocode in the 1993 part 1.5. You can watch the table. You can see first that on the bottom we have a value of K sigma, that is 4 if the stress distribution is uniform. This case is treated in the first line of the table. You can see that sigma 1 is equal to sigma 2, and in this case psi is equal to 1. In this case B effective is equal at rho multiplied by B bar, and in this case BE1 and BE2 are equal to 0.5 multiplied by B effective. So rho takes the value of 0.5. On the right, you have the value of rho and lambda p bar that we have demonstrated in the previous slide. Okay, now we have a global view of a procedure to calculate and to take into account the buckling in the flange part in compression. First, you have a geometry of a profile. It is the drawing on the top on the right. And we know B. If we don't take into account of the corners, we have to remove the corners, and for that we obtain BP, and BP is equal to B minus 2GR, and the formula of GR is given here. Of course, this formula is function of the radius R of the corner and about the pitch phi of the web. When we know BP, we calibrate the raw material in function of the real Fy of the profile. It is the expression of epsilon. As we study a compressed part with uniform compression, we have psi equal to 1, and we know now that K sigma is equal to 4. After we find the formula of lambda p bar, function of the square root of Fy divided by sigma critic, and it is the expression that we have demonstrated some slide before. And after, we have a criteria to define rho. Rho is equal to 1 for lambda p bar inferior to this formula, and rho is equal to lambda p bar minus 0.055 in bracket 3 plus psi divided by lambda p bar square if lambda p bar satisfies this criteria. By this way, now we know we have a solution to determine rho and to calculate B effective of a profile. In the case of Austin compression elements, we have the same type of table given in the Eurocode, part 1.5, and we apply the same methods. Prudence, the value of rho are a little bit different, as you can see on the top on the right. Again, we have the same procedure, and we'll not repeat it, but it is exactly the same approach. Notice that the value of rho are changed. All the rest remain equal. Okay, now we are going to study the plane elements with intermediate stiffener. When you have a plate element with a big length, you have a flexibility of this plate element. To solve this problem, we add a stiffener. And here you have an example of a centrum stiffener. To modelize this situation, we suppose that this stiffener is equivalent to the spring uniformly distributed, and the rigidity of this spring is K. In this case, in the centrum, we can have a beam on continuous spring submit to normal effort in compression. So we can study the buckling of this beam, find a critical stress, sigma critic, find a key coefficient, and finally reduce the thickness of the sheet in the area of this stiffener. This procedure is given on the right. Now we are going to study the mechanical model to take into account of the local web instability. In the Eurocode, 3 situations are described. The first, we have a web without any stiffener. After we have 1 stiffener, and after we have 2 stiffeners. You can see that each time you have lengths that are defined, S efficace 1, S efficace 0 for the first drawing, for example. we have EC, E and this C, that is the position of the neutral axis of the section. In the framework of this presentation, we will study the case of the web without any stiffener. So, we have a drawing on the right. In this case, the Eurocode gives two values, S efficace 0 and S efficace n, that allow you to calculate, in fact, the part of the web that are completely effective. Now, the method to calculate the web effective. First, you determine the position of E and this C, that is the position of a neutral axis. So, on the top of the profile, we are in compression, on the bottom of the profile, we are in tension, and at the line of EC, we have zero stress. When we know this part, we know, in fact, EC divided by sinus phi. Sinus phi is the angle of the web. And we can also calculate S efficace 1 plus S efficace n. Step 3, we determine whether the web is effective or not. For that, if EC divided by sinus phi is superior to S efficace 1 plus S efficace n, then the web is not fully effective. If EC divided by sinus phi is inferior to S efficace 1 plus S efficace n, then the web is fully effective. If the web is not fully effective, a part of the web has to be removed according to the following formula. The first formula, in fact, is the difference between EC divided by sinus phi minus S efficace 1 plus S efficace n, and in bracket, multiplied by t, the thickness of the web. So, if the web is not totally effective, we will carry out a fictive hole to take into account of this problem. And the choice is made by comparison of the distance EC divided by sinus phi with the quantity S efficace 1 plus S efficace n that represents the resistance of the web without buckling. Now we are going to study the formula to determine the span bending resistance of the sheeting profile. Okay, we have a table here that must be done to calculate the effective section modulus W effective. On the bottom of the left, you have a sketch of an half of a rib of a profile. You can see B effective, SW, B bottom, and the axis Y. So, in the first column, you have L in bracket millimeters, and for each part of the profile, you will write here the length of the profile. For example, for the top plate, we have B effective. For the web, we have SW, and for the bottom, BB. After, we have to determine Y. Y is the position of the plate element from the top of the profile. Of course, it's 0 for the top flange, and it will be HW divided by 2 for the web, SW, and it will be HW for B bottom. And after, we have only to calculate, we've made some mathematics, the product of L multiplied by Y and the product L multiplied by Y squared. After is the value of L11, Ly11, and R11. We make the summation of this value. And to obtain the position of the neutral axis, it is a statical moment. We make the sum of the product L multiplied by 1, and we divide it by the sum of the L. By this table, now, we know the position of the neutral axis E, and this is C. After, we must apply the procedure concerning the web. If the web is totally effective, the value of delta in the table will take the value of 0. If the web is not totally effective, we have to make a fictive hole, and delta will take a value, and we will decrease the global result of this value. So we correct the table, and after we have now the possibility to calculate the effective inertia of the profile by using the Huygens formula that is given on the bottom. I remember you that we study an half of a rib. That is why to cover a global rib, it is necessary to multiply the result of the effective inertia by 2. And don't forget to multiply by t if we make the calculation of the length only and not on the area of each part of the profile. Okay, we know now the effective inertia of the profile by rib, and we would like to know the inertia effective of the profile by unity of length. So we divided E effective by rib by B and this R. B and this R is the distance between two consecutive ribs. And now we are ready to calculate W effective. W effective is the minimum of the effective inertia divided by ZC, or inertia effective divided by HW minus ZC. ZC is equivalent, is equal to E and this C. Okay, after all this calculation, we arrive at the interesting point, that is the bending capacity of a profile. So now we know W effective, that is the effective section modulus. We multiply this value by FYB, that is the yield strength of the material, and we divide it by gamma M0, that is the security factor of the system. And finally, we obtain MCRD, that is the resistance moment of the profile. On the sketch on the right, you can see the HW, the stress, sigma 1 and sigma 2. You can see the effective of the part of the profile and the result and the bending moment corresponding. Okay, now we are going to determine the formula of the resistance on the support reaction. As we are in the design by calculation, as we use the Eurocode, we have first, you remember, that to respect the field of application of this formula. The field of application of this formula is given here in 3 points. First, you have to verify that the R divided by T is inferior to 10. R is the radius of curvature of the corner of the profile. HW is the divided by T. HW is the height of the profile. And this criteria, HW divided by T, must be inferior to 200 sinus phi. Last point, you have to verify that the angle of the web is between 45 degrees and 90 degrees. If all these criteria are respected, you can use the formula given in the Eurocode. And that is the formula given in the Eurocode to determine the local transverse resistance. Okay, now we are going to study the reaction capacity of a profile. Here is the formula given in the Eurocode. This formula is issued of lot of tests done in the past. You can see that a lot of coefficients must be determined. First, coefficient alpha. Alpha is in function of a category of profile. You have two categories, category 1 and category 2, and we will see just after what are these categories. So imagine that, for example, we have a sheeting in category 1. In this case, alpha takes the value of 0.075. After we have T. T is the thickness of a profile. After we have FYB, that is the yield strength of a raw material that constitutes the profile. E is the Young modulus of the raw material. After we have LA, again, LA is function of a category of profile. LA is the fictive length, the fictive width of the support. And of course, we have phi, that is the pitch of the web. You can see this on the drawing on the top on the right. And we have gamma M1, that is the safety factor. Okay, now we will study what are these categories 1 and 2. So category 1 corresponds to an end support. And you can see that LA in this case is S and this is S. If we are on an intermediate support, we are in category 2. You can see this on the bottom of the table. And again, the length LA is SS. And if we have a cantilever, in this case, we are also in category 2, and it is in the middle of the table. Now we are going to study the formula to determine the interaction between the support bending and support reaction. I remember you that we have studied MCRD, the bending resistance of a profile. We are studying just before RWRD, that is the reaction to the support resistance of a profile. We have now MED, that is the bending moment that corresponds to the action applied to the profile. And we have FED, that corresponds to the reaction to the support due to the load applied to the profile. And we have two criteria. MED divided by MCRD must be inferior or equal to 1, and FED divided by RWRD must be inferior to 1. But we have also an interaction between the bending moment and the action on the support at an intermediate support. And in this case, we have to respect the last condition. MID divided by MCRD plus FED divided by RWRD must be inferior to or equal to 1.125. If we put this criteria in an interaction diagram, we obtain the interaction diagram on the right. On the bottom we have R, the reaction capacity on the support. On the top we have M, the bending moment resistance, and the acceptable area it is drawing here. Now we are going to study the formula to determine the shear resistance of a sheeting. First, we have to calculate the slenderness lambda bar W, and the formula is given here. After, in function of this value, we go in the table below and we find which value we must take for the stress FBV. For example, if lambda B bar is inferior to 0.83, and if we are in the case of a web without stiffening at the support, In this case, FBV takes the value of 0.58 FYB. When we know this value of FBV, we put this in the formula on the top on the right. FBV is known. We multiply by T the thickness of the profile. We multiply by HW divided by sinus phi, that is the pitched length of the profile. And we divide it by gamma n, the effective factor. And by doing this, we obtain VBRD, that is the shear resistance of the profile. Generally, this shear resistance is above the reaction to the support. That is why, very often, this value is not checked. Okay, now we are going to study the designing of a liner tray. As we have in the design by calculation, you have to respect the field of application given in the Eurocode. When we calculate a liner tray, so we have to be sure that T nominal, the nominal thickness of the liner tray, is between 0.75 mm and 1.5 mm. You have to be sure that B and this F, that is the length of the top flange, must be between 30 mm and 60 mm. You have to be sure also that the H of the liner tray must be between 60 mm and 200 mm. The white flange, BU, must be between 300 mm and 60 mm. We have also to verify that the inertia ER of the reducer of the stiffener of the liner tray divided by BU is inferior or equal to 10 mm/4. And S1, the famous distance S1, is blocked to 1 meter in the Eurocode. And you remember, that is why in the GRISPR project we study this S1 superior to 1 meter to cover the real distance between the spacer that can be 2 meters or more. And here you can see 3 examples on the right of liner tray. 2 cases now to design a liner tray. We have 2 cases. The first is white flange in compression, and another concerns the white flange in tension. For the white flange in compression, you have here an half of a liner tray with a definition of H, the height of a liner tray, BU divided by 2, E0, that is the position of the neutral axis, and BT, that is the length of the top flange of a liner tray. We have a distribution of stress given in the bottom, and you can see that the bottom of a liner tray, we have a hole in the web, so this part is in compression. That is why we have ZC, the position of a neutral axis. So in this case, the bottom of a liner tray is in compression, the top of a liner tray is in tension. And after, we have to apply all the methods, all the design by calculation that we have seen before to calculate the effective width of each part, to determine W effective, and to calculate the MCRD of the liner tray. The same approach must be done for white flange in tension. If you watch the drawing on the bottom of the right, you can see that this time it is the top of the liner tray that is in compression. That is why we have fictive hole of the top flange, fictive hole in the web. We have the position of ZC, the position of the neutral axis, and the stress distribution. Again, we have to do the calculation as we have done before. One changement here, it is BU effective of the bottom of a liner tray. This part is in tension, but this part is very long. It could be 600 mm, for example. That is why the Eurocode proposes a formula to define finally what is the real part of this BU that must be used. And this formula must be applied to find this value. Again, don't forget this limitation of 1 meter. Okay, now we are going to design a perforated sheet. The principle is the following. In the area of the perforation, we have to take into account a reduced thickness of the profile. But the field of application of the formula given in the Eurocode is only valid if for an equilateral triangular repartition of a perforation. In this case, if we have an equilateral triangular repartition of the hole of a perforation, we can use the following formula. So, if the ratio D divided by A, D is the diameter of the perforations and E is the spacing between the center of the perforation. So if D divided by A is between 0.2 and 0.9, and if we calculated the gross section property, in this case, we can use this formula of the Eurocode, TA effective is equal to 1.18T in bracket 1 minus 0.9 D divided by A. So, I repeat, if you have an equilateral triangular repartition of a perforation, and if we calculate a gross section property, and if we respect the criteria of the Eurocode, we can apply this formula, and in the area of the perforation, we reduce the thickness of the web or of the section in this part. Another situation concerns this time if we calculate an effective section property. Again, if we respect the criteria d divided by a between 0.2 and 0.9, and if we calculate an effective section property, we have to apply this formula in the area of the perforation. If now we calculate a single web, submit to a local transverse force, we have to apply this formula. Okay, now we are going to study the deflection. In all the cases, the maximum deflection of a profile calculated with effective inertia must stay below the maximum accepted deflection as defined by the Eurocode. It is possible to make a calculation with several sections characterized by different effective inertia. So, you have a profile submitted to, for example, on two supports. This profile is submitted to downward loading. It takes a deflection. To calculate the deflection of this profile, we will use the E effective of this profile. We calculate this deflection, and we verify that this deflection is inferior to the maximum deflection defined in the national annex of the Eurocode. If we want to optimize the calculation, in this case, we calculated in several sections the effective inertia, because in each section the stress due to the bending moment change. So we calculate for each section the effective inertia, and by integration we calculate the real deflection of a profile, and again we compare this real deflection of a profile with the maximum deflection defined in the Eurocode. Okay, now we are going to see all the cases that are not covered by the Eurocode. For all these type of profiles, the decking embossment, the outward stiffness, the curved profiles with and without arch effect, the assembled profiles on supports, the corrugated profiles, the liner tray with S1 superior to 1 meter, for perforated profiles with a square pattern perforation, for flange hole profiles, for plank profiles, for all these cases that are not covered actually in the Eurocode, you have now some possibility and some design calculation that are defined in the GRISP Plus project. You can see on the right a drawing of each of these profiles. So to understand how to design these profiles, it is necessary for you now to go at each e-lecture done for each of these profiles. Okay, now some view on the bibliography used to carry out this e-lecture. So first, you can see the several parts of the Eurocode, part 3, part 5, that allow to design the Eurocode. After, you can see the standard concerning the CE marking of the profile, about the erection of the building, about the raw material. If you want to go in detail about the method, to know more about the design method, you can see the deliverable of the GRISP Plus project, and you will know more. Thanks for your attention, and don't hesitate to go at the next e-lectures.